You're listening to Audiology. Support our work on Patreon and be sure to submit your requests for topics in the comments below. The term Little Ice Age refers to a period of cooler temperatures, mainly affecting the North Atlantic region, and should not be confused with a full-scale ice age that impacts the entire planet. This concept was first named as such by François E. Matthes in a 1939 paper. Traditionally, scholars mark the Little Ice Age as occurring between the 16th and 19th centuries, although there is debate with some experts favouring an extended timeline from around 1300 to 1850. According to observations by NASA Earth Observatory, the era featured three distinct chilling phases, beginning around 1650, then near 1770, and the last one starting in 1850, with each cold spell separated by brief warming periods. The Intergovernmental Panel on Climate Change's third assessment report suggested that the Little Ice Age was characterized by weather changes that were largely regional, rather than a uniform global shift towards extensive glaciation. The report suggested that the Northern Hemisphere experienced only a mild cooling effect during that era. Various theories have been proposed to explain the Little Ice Age, including periodic decreases in solar radiation, an increase in volcanic activity, shifts in ocean currents, changes in Earth's orbit and axial tilt, also known as orbital forcing, naturally occurring fluctuations in the climate, and significant population declines resulting from events like Genghis Khan's conquests, the Black Death, and diseases introduced in the Americas by Europeans. It's challenging to pinpoint the exact start of the Little Ice Age, as experts have multiple theories. Indicators suggest a cooling period may have begun as early as the 13th century, when sea ice began expanding in the North Atlantic, and Greenland's glaciers started growing, an observation supported by various global accounts of glacier growth. Research conducted by Miller and colleagues in 2012, which used radiocarbon dating on approximately 150 samples of dead vegetation under ice caps on Baffin Island and Iceland, concluded that there was a rapid onset of cool summers and ice formation between 1275 and 1300, with more severe conditions from 1430 to 1455. However, data on glacial lengths indicate a relatively stable climate from the 1600s until the 1850s, followed by a notable glacial retreat. Therefore, identifying the beginning of the Little Ice Age could relate to any period within a 400-year time span. Around 1250, marked by the increasing pack ice in the Atlantic, potentially related to or intensified by the enormous eruption of the Samalas volcano in 1257. Between 1275 and 1300, as evidenced by radiocarbon-dated plant material destroyed by advancing glaciers. Around 1300, when Europe began experiencing inconsistent warm summers. Around 1315, coinciding with the Great Famine caused by persistent rains. Between 1560 and 1630, marked by the global expansion of glaciers known as the Grindelwald fluctuation. The year 1650, which does not signify the beginning, but represents the peak cold phase within the Little Ice Age, also referred to as the first climatic minimum. The conclusion of the Little Ice Age is commonly placed in the late 19th or early 20th centuries. The sixth report of the Intergovernmental Panel on Climate Change characterizes the coldest phase of the last millennium as a multi-century period of relatively low temperatures starting around the 15th century, with global mean surface temperatures averaging minus 0.03 degrees Celsius, ranging from minus 0.30 to 0.06 degrees Celsius between 1450 and 1850 relative to 1850 to 1900. During the early 14th century, there were two notable occurrences when the Baltic Sea completely froze over. These years were 1303, and from 1306 to 1307, this period was followed by an era characterized by unusual weather patterns that included cold temperatures, stormy conditions, and persistent rainfall, as well as a noticeable increase in the water level of the Caspian Sea. Known as the Little Ice Age, this climatic event led to notably colder winters across regions of Europe and North America. In the Swiss Alps, the mid-17th century was marked by the destruction of farms and villages due to the advance of glaciers. In Great Britain and the Netherlands, deep freezes of the canals and rivers were common, becoming popular venues for ice skating and winter festivals. With winters extending up to 5 months, merchants adapted by fitting their flat-bottomed boats, known as bore-style boats, with planks and runners to create ice boats, allowing trade to persist through the frozen seasons. The River Thames hosted its first frost fair in 1608, with the last recorded one occurring in 1814. Changes in infrastructure have since made such events less likely. Historically significant is the march of the Swedish army across the frozen Great Belt in 1658 as they made their way to attack Copenhagen in Denmark. The 1794 to 1795 winter was especially severe, with the French invasion army under the leadership of Pichegru traversing frozen rivers in the Netherlands, and a Dutch fleet ensnared by ice at Den Helder harbour. Iceland also faced challenges during this time, with extended sea ice impeding shipping in harbours. Following the Laki eruption in 1783, Iceland's population was reduced by half, which may be attributed to skeletal fluorosis. There were failures in cereal crop production, leading the population to stray from a grain-focused diet. Earlier, by the early 15th century, the Norse colonies in Greenland had disappeared due to starvation and extreme winters that made agriculture and livestock maintenance untenable. Greenland remained largely isolated by ice from 1410 until the 1720s. In the massif central of France, specifically in the Iseron Basin, a reduction in river activity between 1620 and 1740 coincided with droughts in the western Mediterranean region. Additionally, during the Little Ice Age, southwestern Europe experienced increased wind-driven sediment accumulation attributed to a negative North Atlantic oscillation combined with higher aridity. In 1995, Hubert Lamb, an early climatologist, documented the period's unusually heavy and persistent snowfalls. Lisbon, Portugal, for instance, experienced several snowstorms during a single 17th-century winter. Europe's weather during the Little Ice Age was characterized by its inconsistency, with the Grindelwald fluctuation from 1560 to 1630 signifying a rapid cooling phase that introduced erratic weather patterns. Agriculture across Europe had to be modified to cope with a shorter and less predictable growing season, resulting in frequent famines. Although the Great Famine of 1315 to 1317 may predate the Little Ice Age, subsequent famines in countries such as France, Norway, Sweden, Estonia, and Finland during the late 17th century led to significant population losses. The colder climates resulted in the decline of viticulture in northern regions and severe storms that caused flooding and loss of life, with some areas on the Danish, German, and Dutch coasts being permanently submerged. The Little Ice Age also coincided with cultural adaptations, such as the invention of the violin by Antonio Stradivari, whose instruments may have benefited from denser wood due to cooler climates. James Burke, a science historian, noted the period's impact on everyday life, with innovations like the introduction of buttons and buttonholes and the knitting of custom undergarments for better insulation. Common rooms previously warmed by open fires were replaced with homes featuring multiple rooms and chimneys. Anthropologist Brian Fagan, based at the University of California at Santa Barbara, detailed in his book, The Little Ice Age, how European peasants endured hardships such as famine, cold, revolts, and oppressive rulers from 1300 to 1850. The late 17th century saw significant agricultural decline, with people in alpine regions having to resort to eating bread made from a mix of nutshells, barley, and oat flour. Historian Wolfgang Behringer has suggested there is a connection between the intensity of European witch hunts and agricultural struggles during this cold period. Dagmar Degroot, an environmental historian at Georgetown University, explains in The Frigid Golden Age that the Little Ice Age influenced different societies in various ways, with some, like the Dutch Republic, ingeniously exploiting the changed conditions for commercial and military benefits during their 17th century Golden Age. The Dutch managed to adapt, surviving and even thriving amid the devastating climate that afflicted neighbouring countries, making the most of the opportunities that arose from harvest failures, wind shifts, and inventing new technologies to capitalize on the colder weather. Scholars have widely discussed that during the Little Ice Age in Europe, people often resorted to violence as a way of coping with the harsh conditions that ensued. Europe faced extended periods of cold and dry weather, causing severe droughts that led to failed crops, livestock death, and a greater spread of diseases, these environmental challenges coincided with and exacerbated social and economic strains, including joblessness, which spiraled into a vicious cycle of poverty and poor health. Despite communities having backup strategies such as diversified crops, reserve grain supplies, and global food trade, these measures often fell short. As a result, there was a surge in crimes of desperation, such as theft and homicide. Furthermore, incidents of sexual crimes like adultery, bestiality, and rape increased as society sought to find culprits for their suffering. In trying to make sense of the widespread famine, illnesses, and social turmoil, Europeans unjustly pinned the blame on vulnerable individuals. Studies suggest that hostility towards minority populations, deemed responsible for the cold, dry conditions, intensified during the harshest weather periods. One particular form of scapegoating during this period was the return of witch trials. Researchers Oster in 2004 and Beringer in 1999 both argue that this uptick in persecution was a direct result of the deteriorating climate. Witchcraft, once considered inconsequential, took on new significance in the eyes of Europeans from the 1380s, coinciding with the onset of the Little Ice Age, as they began to associate magical practices with influencing the weather. Witch hunts became systematic from the 1430s, and by the 1480s it was a common belief that witches were responsible for meteorological misfortune. The frequency of witch trials was linked to climate fluctuations, with the most severe periods of persecution corresponding with food shortages in 1570 and the prolonged 1580s crisis. The majority of the accused were impoverished women, often widows. Despite some disagreements over the witches' actual ability to control the weather, the dominant view by the mid-13th century was that they could indeed manipulate natural forces. Jews, too, were blamed for their indirect connection to the consequences of the Little Ice Age. Waves of anti-Semitism swept across Western European Christian societies, particularly during disease outbreaks, such as the Black Death. Jewish communities were accused of well poisoning or associating with lepers who did so, resulting in mass violence against them. This forced many Jews to either convert to Christianity or to seek refuge in places like the Ottoman Empire, Italy, or the Holy Roman Empire, where their beliefs were more tolerated. Furthermore, broader divine discontent was often seen as the cause for the climatic deterioration and its dire effects. This led to strict impositions on social behaviors, particularly those thought to be sinful, with regulations in Germany targeting gambling, drinking, and modest dress, among other activities. This had a disproportionate impact on the lower classes and on women. In Ireland, the Catholic population blamed the Protestant Reformation for inciting the wrath of God, evident in the poor weather. The Annals of Lochsay famously condemned the midsummer snowstorm of 1588 and attributed it to the heresy of the Protestant Bishop of Elphin, John Lynch, stating that a wild apple was not larger than each stone of it. William James Burroughs delves into the artistic representation of winter, highlighting the surge of such imagery in paintings from 1565 to 1665, a period coinciding with a general cooling of the climate from the year 1550. Burroughs suggests that this trend might have been spawned by the particularly brutal winter of 1565, which possibly stirred prominent painters to depict novel winter scenes. He believes the subsequent decline in winter-themed art can be ascribed both to the exhaustive treatment of the subject and to an interruption caused by milder winter seasons. Historical artifacts like illuminated manuscript cycles, notably the Labours of the Months in Books of Hours, have adeptly incorporated wintry elements from as early as the 15th century. The Très Riches Heures du Duc de Berry, crafted between 1412 and 1416, exemplifies such mastery, as February is visually depicted with snow. Back then, the absence of standalone winter landscapes is not unexpected, given that landscape painting had not yet emerged as a distinct genre. Dutch Golden Age painting embraced snowy landscapes and tempestuous maritime scenes, particularly during the most frigid and turbulent era of the Little Ice Age. Modern scholars often interpret these works as laden with symbols and hidden meanings apparent to those of the period. Peter Bruegel the Elder's iconic winter landscapes, including The Hunters in the Snow, from around 1565, embody this period. His artwork, thought to be part of a series called The 12 Months, was specially commissioned by an Antwerp patron, Nicolaes Jongelink. Peter Bruegel the Younger, his son, later replicated several snowy scenes. But according to Burroughs, his works lack originality, casting doubt on their ability to offer insights into winter influences during 1570 to 1600. Bruegel the Elder's Hunters in the Snow is noted to be a fantastical composition, perhaps inspired by his earlier alpine travels, as it was painted in a location without such mountains. Hendrik Averkamp rejuvenated the winter landscape genre in Dutch Golden Age paintings after 1609, with a significant wave of creation occurring between the 1640s and 1660s, paralleling climatic data from that time. Yet, a decline in such depictions post-1660 does not align with any documented easing of winter harshness, implying shifts in artistic preferences or trends. In the late 18th to early 19th centuries, artists once again found favor in wintry themes. Research by Hans Neuberger, scrutinizing 12,000 paintings from 1400 to 1967 for cloudiness and gloom, corroborates a rise in these motifs that align with the timing of the Little Ice Age, particularly its zenith, from 1600 to 1649. In Scotland, paintings and other records document the popularity of winter sports such as curling, ice skating, and ice sailing. Curling has origins in the 16th century and achieved widespread acclaim by the mid-19th century. The sport's outdoor appeal persisted until an outdoor curling pond in Gourock, built in the 1860s, was forsaken in 1963 due to a preference for indoor rinks, vandalism, and warmer winters. The 17th century in Europe was a tumultuous time, marked by a series of distressing events that were in part exacerbated by the harsh climate conditions known as the Little Ice Age. During this period, referred to as the General Crisis, the cooler temperatures led to widespread harvest failures and economic distress, contributing to high levels of death and widespread violence among different groups. The societal upheaval seemed to correlate with the climatic downturn, often manifesting in violent conflicts about 15 years after the onset of cooler weather. One of the most significant armed confrontations of this time was the 30 Years' War, which began in 1618, primarily as a dispute over who would rule Bohemia, but quickly spiraled into a wider religious conflict between Protestants and Catholics within the Holy Roman Empire. This large-scale war soon grew to encompass much of Europe, drawing in all of the main powers of the era. It took an incredibly heavy toll on the territories now known as Germany, with some areas experiencing population declines of up to 70% by the time the conflict concluded in 1648. The devastation impacted the demographics, economy, and social structures of the affected regions for generations to come. European explorers and settlers who came to North America described enduring extremely harsh winters. Samuel Champlain, as noted by Lamb, observed ice on the shores of Lake Superior in June of 1608. The winter of 1607 through 1608 was harsh for both Europeans and Native Americans in Maine, leading to higher death rates, and settlers in Jamestown, Virginia, also reported severe frost. Native American communities formed alliances to address the food shortages caused by these conditions. Pierre de Troyes, a French explorer, documented in his 1686 journal that James Bay was so filled with floating ice on July 1st that he could conceal his canoe behind it. In the notably cold winter of 1780, New York Harbor froze over, allowing people to cross from Manhattan Island to Staten Island on foot. By the end of the 19th century, the ranges of mountain glaciers had been charted. In both the northern and southern temperate zones, the equilibrium line altitude was approximately 100 meters lower than in 1975, indicating more extensive glacial coverage. Glacier National Park experienced its most recent glacial growth in the late 1700s to early 1800s. John Muir discovered in 1879 that the ice in Glacier Bay had receded by 48 miles. Temperature fluctuations in Chesapeake Bay, Maryland, around this time might have been linked to shifts in the North Atlantic's thermohaline circulation. The Little Ice Age coincided with the early European colonization of the Americas, hampering colonization efforts As the settlers confronted a North American climate with hotter summers and colder winters compared to Europe at the same latitudes, particularly in areas like Canada and the northern US, the settlers were unprepared for these conditions, and many early European settlements in North America failed as a result. During Jamestown's colonization, it was one of the chilliest times in the preceding millennium, as historians concur. North America also experienced severe droughts during the Little Ice Age, including the worst drought in 800 years when settlers arrived at Roanoke. University of Arkansas tree ring studies reveal a 7-year drought period, starting when many colonists first arrived. These droughts lowered Native American population numbers and led to conflicts over scarce food supplies. At Roanoke, English colonists demanded food from the Osamokumak, which escalated into warfare and the destruction of native towns. A similar cycle of conflict, exacerbated by the cold weather and the spread of diseases, occurred repeatedly at Jamestown. In 1642, Thomas Gorges described the extreme weather conditions faced by colonists in Maine, including lethal heat in June 1637, and an piercingly intolerable winter in 1641 through 1642, which froze Massachusetts Bay to the extent that horse carriages could travel where ships normally sailed. The short, cold, and wet summers of 1638 and 1639 worsened food shortages, while crops were ravaged by pests like caterpillars and pigeons. Gorges's report highlights a period of erratic weather with high precipitation, droughts, and episodes of extreme cold or heat. Colonists had various theories for the stark weather differences between North America and Europe. Ferdinando Gorges speculated the cold was due to ocean winds, while Humphrey Gilbert suggested the Earth drew cold vapors from the ocean westward. These various observations and theories from inhabitants offer a glimpse into how the Little Ice Age's impact was rationalized and understood in North America. Researchers examining various climate indicators in Mexico's Yucatan Peninsula have offered evidence supporting the occurrence of the Little Ice Age in that area. Their findings align with historical records from both the Maya and Aztec peoples, which describe periods marked by cooler temperatures and drought. Converted. Researchers examining various climate indicators in Mexico's Yucatan Peninsula have offered evidence supporting the occurrence of the Little Ice Age in that area. Their findings align with historical records from both the Maya and Aztec peoples, which describe periods marked by cooler temperatures and drought. Raw. In a separate investigation, multiple sites across Mesoamerica, including Los Tuxtlas and Lake Pompel in the state of Veracruz, Mexico, were studied for changes in past human activity during the Little Ice Age. Evidence of reduced human presence was gathered through the analysis of charcoal residue and maize pollen concentrations in sediment samples collected with a non-rotating piston corer. These findings coincide with signs of volcanic eruptions during the period 650 to 800, which led to the revival of forests in the area. The record of volcanic activity around Lake Pompel has revealed fluctuating temperatures throughout the Little Ice Age in Mesoamerica, painting a picture of climate variability rather than persistent cold conditions. Converted. In a separate investigation, multiple sites across Mesoamerica, including Los Tuxtlas and Lake Pompal in the state of Veracruz, Mexico, were studied for changes in past human activity during the Little Ice Age. Evidence of reduced human presence was gathered through the analysis of charcoal residue and maize pollen concentrations in sediment samples collected with a non-rotating piston corer. These findings coincide with signs of volcanic eruptions during the period 650 to 800, which led to the revival of forests in the area. The record of volcanic activity around Lake Pompel has revealed fluctuating temperatures throughout the Little Ice Age in Mesoamerica, painting a picture of climate variability rather than persistent cold conditions. The term Little Ice Age was initially used to describe a period of cooler temperatures, primarily affecting Europe and North America. But there is also evidence to suggest similar climate changes in other parts of the world, though with different timings and impacts in each area. As explained by Michael E. Mann, while there is evidence that many other regions outside Europe exhibited periods of cooler conditions, expanded glaciation, and significantly altered climate conditions, the timing and nature of these variations are highly variable from region to region, and the notion of the Little Ice Age as a globally synchronous cold period has all but been dismissed. In China, the cold climate led to significant agricultural shifts, including the abandonment of citrus crops in Jiangxi province, which had been cultivated for centuries. Concurrently, the Guangdong region faced an increased frequency of typhoons during the 17th and 19th centuries, times that lined up with particularly arid and cold conditions in the north and central parts of China. Researchers have linked the end of the Ming dynasty partially to the destructive climatic impacts of the Little Ice Age, such as droughts and famines. Historians and scholars generally divide the Little Ice Age into three primary cold phases occurring around 1458 to 1552, 1600 to 1720, and 1840 to 1880. The U.S. National Oceanic and Atmospheric Administration has indicated that the eastern monsoon area of China felt the onset of the Little Ice Age as early as 1560, lasting until 1709, while the western regions near the Tibetan Plateau experienced significant cold later on, from about 1620 to 1749. A weakening of the East Asian summer monsoon due to the cooling of the Eurasian landmass led to colder, drier conditions in southwest China and more precipitation in the northwest. Coaching Chu's analysis from 1972 marked the transition from the Ming to the Qing dynasty as one of the coldest periods in Chinese history, with numerous droughts and freeze events causing severe disruption to food production. Manchuria was hit by famine due to heavy snowfall, which devastated agriculture and livestock. These hardships fueled resentment towards the Ming dynasty's tribute demands, eventually contributing to the rise of the later Jin dynasty and the fall of the Ming dynasty. After the establishment of the Qing dynasty, the early reign of the Kangxi emperor persisted during colder than normal years. Nevertheless, his effective reforms led the way out of the disaster-stricken period, ushering in a time of recovery and prosperity during the High Qing era. In the Himalayas, glacial maximums, dated through methods like surface exposure dating, suggest that the peak of cold conditions occurred between 1300 and 1600, prior to the Northern Hemisphere's coldest stage. There has since been an almost uninterrupted glacial recession. Lastly, both the Baloch people of Balochistan and the residents of Reban Island experienced notable periods of cooling that aligned with the Little Ice Age, leading to significant migrations and environmental changes in their respective regions. Between the 14th and 19th centuries, the African climate was affected by the Little Ice Age, which brought about a general cooling effect across the continent, with temperatures dropping by around 1 degree Celsius on average. In Ethiopia and North Africa during this period, mountains that today have no snow accumulation were reported to have permanent snow cover. Timbuktu, a key trade hub on the trans-Saharan routes, experienced no fewer than 13 significant floods due to the Niger River overflowing, a phenomenon not recorded before or since that era. Research examining southern Africa's paleoclimate indicates considerable shifts in the regional climate and environmental conditions. Studies, including those that analyzed sediment cores from Lake Malawi, point to colder conditions in the duration spanning 1570 to 1820, confirming and expanding our understanding of the Little Ice Age's global impact. Another innovative technique used to assess past temperatures, examining stalagmite growth rates in a chilly South African cave, implied a cold phase from 1500 to 1800 that defined the region's experience of the Little Ice Age. According to the stalagmite Delta 18 oxygen record, spanning a 350-year period, South Africa may have experienced a summer cooling of up to 1.4 degrees Celsius, making it one of the coldest places in Africa at the time. Contributing to the climatic fluctuations in this region were the solar magnetic activity and the El Niño southern oscillation cycles. In eastern Lesotho highlands, the Little Ice Age might have re-triggered periglacial landforms. Archaeological findings also shed light on how shifting climate patterns during the Little Ice Age potentially influenced societal developments in South Africa. For instance, the people of Great Zimbabwe, according to these reconstructions, might have thrived relative to competitor societies like the Mupungubwe due to ecological benefits from increased rainfall. Furthermore, pollen records from Hyrax middens in the Cederberg Mountains suggest a rise in humidity at the commencement of the Little Ice Age. Beyond temperature changes, evidence from East Africa indicates that the Little Ice Age had a profound impact on the hydrological cycle, especially in the latter part of the 1700s. Reconstructions using historical data from 10 major African lakes show a significant drought and desiccation episode throughout East Africa. This event led to dramatic reductions in lake levels, sometimes turning them into shallow pools. Consequently, it is believed that water bodies like Lake Chad could be crossed on foot during this period, and intense droughts were ubiquitous. The prevalent dry conditions would have likely forced local societies into mass migrations and conflict with neighbouring groups, as the parched soil rendered agriculture impractical. Kreutz and colleagues, in a study from 1997, analysed ice core data from West Antarctica and drew comparisons with data from the Greenland Ice Sheet Project 2. Their research hinted at a global cooling event occurring simultaneously. The significance of this cooling, as observed in the Antarctic Peninsula's Bransfield Basin sediment core, is underlined by signs of significant climate periods aligning with the medieval warm period and the Little Ice Age. The study highlighted the presence of other similar climatic events, stating, "Other unexplained climatic events comparable in duration and amplitude to the Little Ice Age and medieval warm period events also appear." Furthermore, the Sipel Dome ice core records indicate a climate event that began at the same time as the Little Ice Age in the North Atlantic, verified by matching up with the Greenland Ice Sheet Project 2 data. This event stood out as the most significant climate fluctuation in the Sipel-Dome Holocene glaciochemical record. The core samples from Sipel-Dome revealed the highest frequency of melt layers, reaching 8% between 1550 and 1700, which is attributed to warmer summer temperatures. Complementing these findings, ice cores from Lower Dome showcased reduced concentration of atmospheric carbon dioxide during the period of 1550 to 1800, leading Etheridge and Steele to surmise this was probably as a result of a colder global climate. Meanwhile, sediment cores from the Bransfield Basin indicated a neoglacial episode during the Little Ice Age, inferred from variations in diatom populations and sea ice taxonomic groups. Adding to this, the Mount Erebus Saddle ice core records suggested that the Ross Sea region's average temperatures were approximately 1.6 degrees Celsius lower during the Little Ice Age compared to the past 150 years, with a potential error of plus or minus 1.4 degrees Celsius. Australia's experience during the Little Ice Age deviated from the classic cooling trend observed in Europe and North America because of its location in the southern hemisphere. Instead of cooling, Australia faced a period of higher rainfall and humidity, particularly in the east and southeast regions. Research by Tibby and colleagues in 2018 revealed through lake sediment analysis in Victoria, New South Wales and Queensland that these areas had unusually cool and wet conditions from the 16th to the early 19th centuries. They identified the global Little Ice Age peak lasted from 1594 to 1722, corresponding with their findings. Notably, the Swallow Lagoon indicated heavy rainfall from around 1500 to 1850, with some years surpassing 300 millimeters of rain. However, after 1890, rainfall notably diminished. Lake Surprise's salinity records showed prolonged humidity from 1440 to 1880, turning arid after 1860, signaling a shift in climate. The arrival of the British in 1788, as described by Tibby and his team, brought significant agricultural changes to Australia, particularly in the east where major cities like Sydney, Melbourne and Brisbane developed. New farming practices, including pastoralism, necessitated extensive deforestation and land clearing, graphically depicted in John Glover's 1833 painting Patterdale Landscape with Cattle. These activities had profound ecological consequences by the mid-19th century, including biodiversity loss, soil erosion, and increased soil salinity. Gordon and others in 2003 also highlighted that the clearance of land in Australia led to a 10% reduction in atmospheric water vapour transport. This phenomenon wasn't isolated to eastern Australia, as similar land clearing in Western Australia during the 19th century caused a decrease in rainfall in that region. These colonial agricultural practices likely exacerbated the drought and arid conditions that signified the end of the Little Ice Age in Australia. In northern Australia, dry conditions prevailed, but Great Barrier Reef coral studies suggest that rainfall levels were similar to today's, albeit with less variation. The corals indicated that water vapor movement from tropical oceans to the poles intensified during the Little Ice Age. Borehole temperature reconstruction methods suggest that over the last 500 years, the 17th century was the coldest period for the continent, and Australia's warming has only been about half that of the Northern Hemisphere. Across the Tasman Sea in New Zealand, the Franz Josef Glacier on the west coast of the Southern Alps dramatically expanded, peaking in the early 18th century, a rare instance of a glacier advancing into a rainforest. Tree ring data implies this expansion resulted in a minus 0.56 degrees Celsius, minus 1.01 degrees Fahrenheit, temperature anomaly for New Zealand during the Little Ice Age. Furthermore, lichenometric dating suggests that the neighbouring Möller Glacier reached its maximum around 1725 to 1730. Research pertaining to the sea levels of the Pacific Islands reveals a notable decline during the period spanning from 1270 to 1475, which correlates with a temperature drop of 1.5 degrees Celsius, as identified through oxygen isotope analysis. This temperature decrease was concurrent with an upsurge in the occurrence of El Niño events. Data extracted from tropical Pacific coral formations indicate that the frequency and intensity of El Niño southern oscillation events reached their zenith in the mid-17th century. Examining foraminiferal oxygen-18 isotopes unveiled that the Indo-Pacific warm pool bore warm and high salinity conditions resembling present-day temperatures from 1000 to 1400. Post-1400, the region cooled, reaching its nadir temperatures around 1700, aligning with the shift from mid-Holocene warmth to the cooler period known as the Little Ice Age. In contrast, the adjacent southwestern Pacific underwent warmer conditions throughout the Little Ice Age, purportedly due to augmented trade winds which propelled evaporation and salinity levels in that region. This temperature disparity between the poles and the equator likely contributed to more arid conditions within the subtropical zones. Independent, multifaceted research on Easter Island's Raraku Lake, encompassing sediment analysis, mineralogy, and various geochemical approaches, suggests the island was subjected to two significant dry spells resulting in drought. The first dry phase spanned from 500 to 1200, followed by a more humid interval that lasted from 1200 to 1570, aligning with the heyday of the Rapa Nui civilization. Subsequently, the island faced another arid period during the Little Ice Age, between 1570 and 1720. Analysis of tree rings in Patagonia has revealed periods of cold climate around 1270 and 1380, followed by another cold spell extending from 1520 to 1670, coinciding with climatic events in the Northern Hemisphere. Sediment samples from Puyehu Lake suggest a prolonged wet phase from about 1470 to 1700, an indicator recognized by researchers as marking the beginning of the Little Ice Age in the region. Research presented in a 2009 study points to a trend of cooler and more humid conditions in southeastern South America from 1550 to 1800, using various scientific indicators and models. Moreover, oxygen isotope records from ice cores in the Andes indicate a cooling phase from 1600 to 1800. Historical accounts offer supporting evidence of these climatic changes, albeit less scientifically rigorous. For instance, when the Antonio de Vea expedition navigated into San Rafael Lake in 1675 through what is known as Rio Tempanos, or Iceflow River, they did not encounter any ice flows, and observed the San Rafael Glacier did not stretch deeply into the lagoon. Yet, less than a century later, in 1766, explorers documented the glacier calving into the lagoon, and when Hans Steffen visited in 1898, he noted the ice had considerably advanced into the lagoon. These observations suggest a gradual cooling trend in the region from 1675 to 1898. By 2001, the glacier's borders had noticeably receded from their position in 1675. There is a hypothesis that during the Little Ice Age, essentially from the 17th to the 19th centuries, all glaciers around Gran Campo Nevado near the Strait of Magellan were at their largest extent in the entire Holocene epoch. It's also been posited that this period may have adversely affected marine ecosystems in the area and the practicality of navigating the Patagonian fjords and channels, complicating the maritime activities of the indigenous Kawascar people. The understanding of the Little Ice Age in northern Patagonia is enhanced by these documentary sources, providing valuable, independent confirmation for the event's impact in the region. The period known as the Ottoman Little Ice Age is recognized for a remarkable climate shift in the Northern Hemisphere, spanning from the early 1300s to the mid-1800s, with a particularly severe phase between the 16th and 17th centuries. François E. Matte is credited with coining the phrase Little Ice Age in 1939, referring to a plunging global temperature trend from the 1500s to the 1800s. During this time, the Ottoman Empire evolved from a modest band of warriors into a formidable world entity. It was towards the end of the 1500s that signs of the Little Ice Age emerged, profoundly affecting the Ottoman Empire's economic, societal, and cultural landscapes. In February 1621, historical accounts record the freezing of the Bosphorus Strait in Istanbul, signaling extreme climatic fluctuations that also saw severe winter conditions reported by Byzantine writings in 1265, 1277, and the winters of 1297 to 1298. Around 1300, a particularly harsh winter took place in 1298 to 1299 in the Middle East, succeeded by an enduring drought from 1302 to 1304 in Asia Minor, and extensive flooding of the Sangarius River during the summer of 1302. The vast Ottoman Empire, spread across diverse climates and ecosystems, found its agricultural and trade-dependent economy susceptible to the Little Ice Age's grasp. The population had reached an estimated 30 million by the late 16th century, exacerbating land shortages and elevating tax demands. This period coincided with spiking inflation in both the Middle East and Europe. The onset of the Little Ice Age brought grain shortages, a marked deviation from previous abundance thanks to the proximity of the Danube, Nile, and Black Sea, due to shorter growing seasons and diminished harvests. The empire's food security, once underpinned by the agricultural outputs of regions like Anatolia, Syria, Egypt, and the Tigris-Euphrates, was now in jeopardy. This reliance on agriculture carried the risk of political instability, which ultimately emerged as adverse weather patterns persisted and revolt became a last resort for desperate, immobile peasants. Natural catastrophes such as droughts, floods, and storms compounded these issues, leading to shifts in population distribution and nurturing the seeds of new socio-political dynamics within the empire. Amidst the cold spells and droughts, the most significant societal fracture came in the form of the Sellerly Rebellion, around 1596 to 1610. This rebellion, fueled by dissatisfaction and not an outright desire to usurp the government, became the longest-standing domestic challenge in the Ottoman Empire's history. The rebels aimed for governorship roles rather than the overthrow of the state power. The lingering effects of the Little Ice Age left the empire in a debilitated state, not fully recovering until approximately a century later, characterized by diminished population and strength. The Central England temperature record provides the longest, consistent record of temperature measurements in the world, tracing back to the year 1659. This record begins during what's commonly called the Little Ice Age, a period whose definition varies. The information gleaned from the Central England temperature record is critical for understanding the climate patterns of the Little Ice Age. According to the record, there was a notably higher frequency of extremely cold winters throughout the Little Ice Age. These severe winters align with historical records of frost fares on the River Thames and corroborate reports of very low temperatures across Europe at that time. Moreover, the Central England temperature record aligns with broader paleoclimatic data in determining average temperature trends. However, the colder winters were not consistent throughout the Little Ice Age, as evidenced by the Central England temperature record. For instance, the winter of 1684, notorious for one of the grandest frost fares, stands out as the chilliest winter in the entire record. Yet remarkably, just 2 years later in 1686, the Central England temperature record shows that England experienced its 5th warmest winter. As for summers during the Little Ice Age, the Central England temperature record indicates that they were not significantly cooler overall, but when cooler summers did occur, they frequently coincided with volcanic activity. In summary, the Central England temperature record suggests that rather than a uniformly frigid period, the Little Ice Age in Europe should be characterized by its irregular but significant cold winters that brought down the average temperatures. This paints a picture of a complex climate pattern rather than a period of relentless chill. Researchers have proposed a list of 7 potential factors that could have led to the period known as the Little Ice Age. These include shifts in Earth's orbital patterns, a reduction in the Sun's output, an increase in volcanic eruptions, changes in the patterns of ocean currents, and the impact of human population changes on forests, either through expansion or clearing. Additionally, the natural variability of the Earth's climate system itself may have played a role. Solar activity encompasses various disturbances on the Sun, such as sunspots and solar flares, which are linked to changes in the Sun's magnetic field and its corona. The solar wind carries this magnetic field into space, adhering to Alfvén's theorem. Variations in the solar wind's magnetic field can scatter galactic cosmic rays, thus reducing their impact on Earth. Scientists track historical solar activity by studying isotopes like carbon-14 and beryllium-10, which are produced when cosmic rays collide with our atmosphere, and can be found in natural archives like tree rings and ice cores. For example, during the Spora minimum from 1400 to 1550, and Maunder minimum from 1645 to 1715, periods of particularly low solar activity coincided with the Little Ice Age, although the correlation with climate is complex. Solar activity inferred from isotope analysis was actually high between the Spora and Maunder minimums, almost as much as around 1940, despite the period still falling within the Little Ice Age. One hypothesis, suggested by a study analyzing biogenic silica indices, correlates a significant drop in solar activity around 1230 Anno Domini with the onset of the Little Ice Age, predating major volcanic events. McCoy and colleagues' research showed a spike in carbon-14 production at the beginning of the Spora minimum, aligning with a steep temperature decline recorded in European peat bogs. However, the timing discrepancies between solar activity and temperature changes challenge a simple causal link. Judith Lean's 1999 study highlighted a possible connection between the Sun's energy output and the Little Ice Age, proposing that a modest increase in total solar irradiance of 0.13%, or 1.8 watts per square meter, over the period from 1650 to 1790, could have warmed the Earth's surface by 0.3 degrees Celsius. Her team's calculations suggested a strong correlation with 62% explained variance between global temperature and solar irradiance, devising an equation where a 0.1% TSI rise corresponds to a 0.16 degree Celsius temperature increase. The accuracy of longer-term TSI trends remains limited by the quality of space-based radiometry measurements. Modern TSI data and cosmic ray flux comparisons indicate that the Sun's output during the Maunder minimum might have been comparable to or even exceeded modern levels, with a considerable uncertainty margin. Despite fewer sunspots and increased isotope deposition during the Little Ice Age's solar minima, the colder temperatures in the northern hemisphere began before and continued after the Maunder minimum. The varying solar activity did not visibly affect global or northern hemisphere temperatures. Evidence from central England temperature records suggests that low solar activity might have influenced the frequency of cold European winters during the Little Ice Age, whereas colder summers aligned more closely with volcanic eruptions. Ice core data from Greenland imply that solar activity accounted for just over half of the observed climate variation, while climate models show that volcanic action had a more significant influence on the Little Ice Age's temperatures. Orbital changes in the Earth's trajectory around the Sun have gradually cooled the northern hemisphere for the last 2,000 years. This cooling trend, amounting to approximately 0.02 degrees Celsius per century, could continue and potentially lead to an ice age. However, this was abruptly reversed in the 20th century as global temperatures increased, largely attributed to anthropogenic greenhouse gas emissions. The 2012 study by Miller and his colleagues suggests that the onset of the Little Ice Age does not require significant changes in the Sun's energy output, but can be attributed to a series of large volcanic eruptions. They identified a unique period stretching over 50 years, characterized by at least 4 massive volcanic events. Each of these events released more than 60 teragrams of sulfate into the atmosphere, which can scatter solar radiation and lead to a cooling effect on the Earth's climate. Volcanic eruptions can have a profound impact on global temperatures by ejecting ash and sulfur dioxide into the stratosphere. The ash particles impede solar radiation, while the sulfur dioxide transforms into sulfuric acid particles that reflect sunlight, both contributing to a decrease in surface temperatures. A specific example that the researchers pointed out was a particularly intense volcanic eruption around 1257, which might have been Mount Semalis in Indonesia. This was followed by 3 subsequent eruptions over the next few decades. These continuous volcanic activities, including a major mysterious eruption in 1452 or 1453, likely initiated and then reinforced the cooling trend due to their cumulative effect, and the subsequent enhancement of sea ice and ocean interactions that helped sustain cooler temperatures. Several other volcanic eruptions throughout the Little Ice Age period could potentially have played a role in reinforcing this cooling trend. These include eruptions from Billy Mitchell around 1580, Huayna Putina in 1600, Mount Parker in 1641, an eruption in Long Island in Papua New Guinea around 1660, and Laki in 1783. One of the most infamous eruptions was that of Mount Tambora in 1815 in Indonesia, which led to such a significant climate disruption that 1816 became colloquially known as the Year Without a Summer, with frost and snow reported in the summer months in regions as far apart as New England and Northern Europe due to the ash and aerosol particles in the atmosphere. During the early 21st century, scientists suggested that the Little Ice Age might have been influenced by a decrease in ocean circulation, particularly due to a less forceful North Atlantic gyre. It has been hypothesized that before the Little Ice Age, a period of relative warmth known as the medieval warm period could have led to an influx of fresh water into the North Atlantic. This potentially disrupted the thermohaline circulation, which some experts believe might classify the Little Ice Age as what's referred to as a Bond event. In 2005, fears were raised about the possibility of a contemporary disruption of this circulation due to modern global warming. More up-to-date research points to the Atlantic meridional overturning circulation potentially being in a weakened state currently, which may be unparalleled in both the Little Ice Age era and possibly the last 1,000 years. However, the scientific community continues to engage in active debates concerning the current state of the Atlantic meridional overturning circulation, with these latest findings casting doubt on the connectivity between the Atlantic meridional overturning circulation and the Little Ice Age. Conversely, there is some research that suggests the Little Ice Age may have been a result of a more regional hindrance in the North Subpolar Gyre's convection. What is particularly noteworthy for contemporary discussions on climate change is that although only a few climate models predict it, there is the possibility of a complete and lasting breakdown of the North Subpolar Gyre convection under certain future climate change projections. Some scholars believe that humans started affecting the climate earlier than commonly thought, as detailed under the topic Early Anthropocene. They argue that significant declines in human populations across Eurasia and the Americas lessened human impact on the environment, leading to a period of cooling. Regarding the Black Death in Europe, this catastrophic pandemic is believed to have wiped out between 30% and 60% of Europe's population. The global population is estimated to have dropped from around 475 million to between 350 and 375 million during the 14th century due to the plague, and it took about 2 centuries for the population to bounce back to its former levels. William Rudiman and fellow researchers have suggested that these substantial population decreases in Europe, as well as in East Asia and the Middle East, led to a decline in farming activities. This, in turn, enabled forests to regrow, which absorbed more carbon dioxide from the atmosphere, resulting in cooling that contributed to the Little Ice Age. As for the Mongol invasions, a 2011 study from the Carnegie Institution's Department of Global Ecology has claimed that these invasions, which spanned nearly 200 years, helped cool the planet. The Mongols killed vast numbers of people, which led to the abandonment of cultivated lands. These lands subsequently returned to forest, increasing the amount of carbon absorbed from the atmosphere and therefore contributing to a cooler global climate. William Rudiman proposed that the dramatic decline in the population of the Americas following the arrival of Europeans in the 16th century may have contributed to environmental changes. Building on this idea, Koch and colleagues, in their 1990 work, argued the European invasions and subsequent diseases, which might have caused the death of up to 90% of Native Americans, led to the rewilding of approximately 50 million hectares of farmland. This reversion to natural vegetation could have resulted in greater absorption of carbon dioxide. Further supporting this notion, several scholars recognize the substantial deforestation carried out by indigenous Americans for agricultural purposes prior to European contact, which, after decimation from European diseases, was reversed. Researchers like Richard Neville and Robert Dull emphasized that the human-induced clearing of forests and setting of fires significantly impacted carbon storage in neotropical forests, including those in the Amazon and Central America, even before Europeans arrived and diseases spread through the Columbian Exchange. Dull and Neville estimated that the regrowth of forests in the tropical regions of the Americas between 1500 and 1650 might have sequestered 2 to 5 petagrams of carbon. Chris Brierley hypothesized that the massive loss of life caused by European-introduced epidemics resulted in widespread abandonment of cultivated land, which in turn paved the way for forests to reclaim these areas and lock away more carbon dioxide. Moreover, sediment core and soil studies hint that this reforestation in the Americas could have played a role in the onset of the Little Ice Age. Connections have been made between this massive decrease in population and a recorded decline in carbon dioxide levels taken from ice core measurements at Law Dome in Antarctica. During the period known as the Little Ice Age, it's thought that large-scale forest clearing had a significant impact on the planet's reflectivity, its albedo, contributing to lower temperatures both regionally and around the globe. When forests in high-latitude areas were cut down, more snow was exposed, which in turn made the Earth's surface more reflective and led to temperature drops due to the increased albedo. This clearing of land was largely for expanding agriculture. A possible explanation for why this deforestation occurred at the scale it did is known as the land use intensification theory. This theory, initially put forward by Esther Boserup, posits that agricultural development is driven by population pressures, suggesting that as populations grew, more land was converted to agriculture, possibly influencing the climate of the time. Despite this theory being a plausible explanation for the climate changes observed during the Little Ice Age, it remains speculative for various reasons. One major obstacle is the challenge in accurately simulating the climate from that era, as data is often limited to specific areas, making it hard to draw conclusions about the full extent of global climate change. Additionally, climate simulations that encompass the Little Ice Age demonstrate both rises and falls in global temperatures, indicating that deforestation at that time can't be pinpointed as the sole or even a consistent driver of the cooling observed. This implies that there were likely many other contributing factors to the climatic variations during that period. Converted. During the period known as the Little Ice Age, it is believed that large-scale forest clearing significantly affected the planet's reflectivity, known as albedo, leading to lower temperatures both regionally and globally. This occurred when forests at high latitudes were cut down, revealing more snow, which in turn increased the Earth's reflectivity and caused temperatures to drop due to the heightened albedo. The main reason for clearing these lands was to expand agricultural activities. The land use intensification theory, first proposed by Esther Boserup, offers a potential reason for the widespread deforestation. This theory contends that the push for agricultural development is a result of population pressures, implying that as populations increased, more land was turned over to farming, potentially affecting the climate at that time. Nevertheless, this theory, while providing a feasible explanation for the climate changes during the Little Ice Age, is still considered speculative for several reasons. A significant challenge is the difficulty of accurately simulating the climate of that era, partly because data is often limited to specific regions, which complicates drawing conclusions about the overall impact on global climate. Furthermore, climate models that include the Little Ice Age show both increases and decreases in global temperatures, suggesting that deforestation during that time cannot be definitively identified as the main or a consistent cause of the observed cooling. This suggests that there might have been multiple other factors affecting the climate fluctuations during that period. Natural shifts in the Earth's climate could potentially account for historical changes in climate patterns. Although determining the exact degree of natural variability is complicated due to the presence of other influencing factors, whose impact might not be fully understood. To probe this natural variability, scientists often use extended simulations with complex climate models that mimic the interactions between the ocean and atmosphere. These models have the advantage of operating without external influences, yet they may not perfectly mimic real-world conditions. Chaos-induced changes within the ocean, the atmosphere, or their interplay are thought to be driving these variations. Despite this complexity, research has indicated that natural variability alone might not explain significant climate events like the Little Ice Age. On the other hand, extreme cold winters experienced from 1770 to 1772 in Europe have been linked to a specific deviation in the North Atlantic Oscillation, suggesting that some historical climate events can be associated with natural anomalies in climate patterns.